Physical science, this is your pre-lesson on nuclear reactions, or what we call nuclear decay. And I just want to make sure that you know that we're dealing with isotopes, and isotopes are going to be the average of different kinds or different versions of elements that we find on the periodic table. So for example, we can have carbon 12, carbon 13, carbon 14, and then the carbon that we see on the periodic table is an average of all three of those isotopes. So isotopes are going to be different versions of the same element or atom. But when we talk about radioactive decay, this is going to be when the isotopes actually change from one element to a completely different element, and they have a number of ways in which they do that. Before I move forward with explaining the different ways in which an element can change into a completely different element, is making sure that you understand that there are two reactions in which isotopes can do that. And that's going to be through what we call fission. Fission is a decomposition reaction where the nucleus splits and we get two different kinds of elements from that reaction. And then we have something called a fusion reaction, which is when very closely related to a synthesis reaction where two nuclei combine or come together to make a new element. And so those are the two types of nuclear reactions, and we'll talk more about those in detail and what they look like in our next video. But then I want to make sure that you understand how through a reaction like this that we can go from one element to another through radioactive decay, or what we call nuclear decay. And you have four kinds of nuclear decay. That is alpha decay. And the two key things to remember about alpha decay is that the atomic number is going to change by 2, or it changes by 2. And then the atomic mass also changes by 4. And so for beta, a beta negative reaction or decay is when the atomic number increases by 1 and the atomic mass will stay the same. And if you are in a beta positive decay or beta positive reaction, the atomic number decreases by 1 while the atomic mass will remain the same. And so in a gamma, which is the fourth one, which is probably the easiest one to remember, is that the atomic mass or the atomic number will not change. So we're going to start over here on this side of the board where we see examples of what we call alpha decay. And so remember, the rule for alpha decay is that the atomic mass is going to change by 4, and the atomic number is going to change by 2. And what you're going to get is the breakdown of a nucleus into the next element and helium. So I need you to be mindful that whenever a nucleus breaks down, like what we're going to see with this uranium, we're going to get the new element plus helium. That being said, the way that we determine what the new element is going to be is by following the rules for alpha decay, which actually says that there's going to be a change in the atomic number by 2, and there's going to be a change in the atomic mass by 4. In this particular instance, we have a change in the atomic mass by 4, and you see that there is a decrease in the atomic mass, and so you get 228. And then there has been a decrease also in the atomic number by 2, and we have an atomic number of 90. And so we know, if this is the case, that this is alpha decay. And so as a result, we know that we need helium to finish out this equation. And so we have to also make sure that we have the atomic number for helium, the atomic mass for helium, and also the atomic number as the subscript, just like we do with all of our isotopes. So just by way of reminder, with an alpha decay, you're going to see a change by 4 in the atomic mass, while you're going to see a change by 2 in the atomic number. And whenever you're finishing out the equation, you're going to end up with helium in the products. So let's take an example of alpha decay if it was written in an actual problem. So we're looking at the isotope, which is thadmium-234, and it's decaying by alpha emission. So that means that this thadmium is breaking down into another substance by way of alpha decay. And so we know that because thadmium is 234 in its atomic mass, we can look at the periodic table and determine the atomic number for thadmium, and that is 90. The atomic number for thadmium is 90, and then we're going to get the yield because we're going to decrease the atomic mass by 4, which is going to be 230, and we're going to decrease the atomic number by 2. We're going to decrease it, so we're going to end up with 88. So if that's the case, we're going to look at the periodic table and determine what element the thadmium is turning into due to the atomic number being 88. And that that element is radium on the periodic table. And then of course we know this is alpha decay, so we're also going to get some helium out of this, and we write the isotope for helium for alpha decay. So now let's move to beta decay. Beta decay is just what we reviewed before. We're going to see an increase in the atomic number while the atomic mass is going to stay the same, and we're going to actually lose an electron, which is why you see the -1 here. We're going to lose 1 electron in the process. And so when we write this, we're going to keep the atomic mass the same, and the atomic number is going to increase by 1. And now we see a complete reaction that has taken place through beta negative decay. So let's say they propose to us this in a word problem or in word form. We have iron 59, and it's decaying by beta emission. So we know that we're going to start off with iron 59 here, and so as we look at this, we have iron, and the atomic mass for iron is 59, and the atomic number is 26. And so in beta negative decay for iron, we're going to keep the atomic mass the same, and the atomic number will change, which is 27, which means that iron is turning into cobalt. And of course, whenever we have beta decay that is negative, we indicate that by the loss of an electron. So we have to do our signal for, or our symbol for, the loss of an electron, which would be the E with the 0 and the -1 next to it. So we're gonna finish up and go with beta plus decay. And so remember, with beta plus decay, the atomic number is going to decrease and the atomic mass will stay the same. So in this case, we have zinc and the atomic mass is 65. The atomic number is 30. So the new atomic number is going to be 29, while the atomic mass will stay at 65. And the new element that zinc is turning into is going to be copper. And so again, whenever we're going from one element to another with beta plus decay, you have to indicate that there has been an electron captured. So of course you're going to have the symbol for the electron capture with the 0 representing the fact that there is no change in the atomic mass. But then we have a +1, meaning that we've had an electron that has been added. So let's just say that we have a beta plus decay word problem. They're requesting that we take an isotope and see how it decays, and in the fact that an electron has been captured. So this right here is going to let us know that we're in beta plus decay. And so we have carbon, which has an atomic mass of 11, and we know that the atomic number for carbon is 6, and we want to see what carbon is going to change into by way of beta plus decay. So we know that in beta plus decay, the atomic number is going to decrease by 1. So the new atomic number is going to be 5. The atomic mass will not change, so it will stay 11, but the new element is going to be boron. And this is by capturing an electron, so we have to represent that by using our symbol with the electron and the 0 representing that there's no change in the atomic mass, while we've had the addition of an electron. In our final form of nuclear decay or isotopic decay is going to be gamma. And with gamma, nothing changes. So the atomic number does not change, nor the atomic mass. You simply express that you're going from the same element that the element doesn't change, so the atomic mass remains 7, the atomic number remains 4, and you indicate that it is gamma decay by putting the symbol for gamma, which is this symbol right here that looks like a Y. So let's say we have an isotope of TC 99, which has an atomic mass of 99 and a atomic number of 43, and we want to see what it's going to decay into. It's going to remain TC99 because the atomic mass does not change. And with gamma decay, neither does the atomic number, but we're going to indicate the decay that is gamma by using the gamma symbol, and that is our final formula for gamma decay. So these are our 4 types of nuclear decays. We'll discuss nuclear reaction, fission and fusion in our next video. Thank you and have a great rest of your day.